In this video, we're going to go over section 6.2 from our textbook, which is on exponential functions. So we'll start with an exponential function of this form here. F of x is equal to a to the power x, where a is some number greater than 1. A function like this has certain properties. First, the graph is of this shape here, where the domain is going to be all real numbers, and the range is all numbers greater than 0. So we'll see that our function is going to be increasing and continuous on its entire domain, and the function is one-to-one. Additionally, we know that all of the output values are going to be greater than 0, and they're not going to cross our x-axis here, so we're going to have a horizontal asymptote on this x-axis. And lastly, we know that our graph is going to pass through these points here for whatever a value we have. So we'll look at an example of this here. We want to graph this function here, f of x is equal to 4 to the x plus 4. So in this case, what we're going to do is use the graph of our parent function, y is equal to 4 to the power x. That's going to be of the same form of this guy here, and then we know we can use graph translations to then find the graph of this guy. So doing some color coding here, we're going to graph this guy using the properties that we just discussed above. So first we know that the graph is going to pass through this point here, 0, 1, for this graph here. So 0, 1 would be right about here. That's going to be our y-intercept. We also know that the graph is going to pass through the point -1 and a to the -1 power. We're looking at this guy, where a is going to be 4 here. So this will be 4 to the -1 is going to be 1 over 4. So that means this point here is going to be -1 and 1 over 4. So that'll be right about there. And lastly, we have a point 1, a, so this will be 1, 4 here. And we know we're going to have an asymptote on our x-axis, so this graph is not going to cross our x-axis, and it's going to look like this here. Alright, now using this parent graph here, we can graph this translated graph. We have 4 to the x plus 4 here. So in this case, this x here is being replaced with this x plus 4, and this change is happening inside the function, so we have a composition of functions. So this tells us that our graph is going to be shifting horizontally, and it's going to go 4 units to the left, since we have x plus 4 here. So we'll graph this guy in green. Shifting this 4 units to the left, we'll start with this point here. So moving this 1, 2, 3, 4, we'll have that point there. Shifting this point now, 1, 2, 3, 4, we'll have another point right about there. And lastly, shifting this one, 1, 2, 3, 4. Our graph will look like this. So since we translated this guy horizontally, this doesn't change our horizontal asymptote, so this guy still won't cross our x-axis. Alright, and then lastly, the domain of our function is just going to be all real numbers. So our function is of this form here, and then our range is also going to be 0 to infinity. Alright, let's look at another exponential function here. So an exponential function of this form, so f of x is equal to a to the power x, where x is going to be in between 0 and 1, has these properties here. So in this case, the graph looks like this guy. Our function is going to be decreasing and then continuous on its entire domain, and this function is one-to-one. We'll also see that the x-axis is again our horizontal asymptote, and the graph passes through these 3 points here. So we'll look at an example of a function of this form. We want to graph f of x is equal to 1/2 to the power x minus 1. So in this case, what we'll do again is use our parent function, our parent graph here, to graph our function here. Now, using all of the information we see above for a function of this form here, we know that the x-axis is going to be a horizontal asymptote, and our graph is going to have somewhat of this shape here. It'll pass through these points. So we'll start with the first point, -1 comma a to the -1. Well, in this case, our a is 1/2. So 1/2 to the -1, just the reciprocal of this guy, so this will be 2. So our point will be -1 comma 2. So right about there. Next, we know we're going to have a point at 0 comma 1. And lastly, we're going to have a point at 1 comma a. So this would be 1 and then 1/2 there. So our graph has this shape here. Again, we have a horizontal asymptote on the x-axis, so we're not going to cross that guy. So this is our function, our parent function, and we're going to use this guy to graph this one here. So we'll do this one in green. And so we know, using our graph translations, that this is just going to be our parent graph here, shifted 1 unit downward. So that's what we'll do for each point that we just found. For example, this point here, we're just going to shift that 1 unit downward. We'll shift this one 1 unit downward. And we'll shift this one 1 unit downward. All right, so our graph will look right about that there. And since we shifted this guy 1 unit downward, this means our original horizontal asymptote, which was our x-axis, is now shifted 1 unit downward. So we'll have a horizontal asymptote at y is equal to -1. All right, and then something else I wanted to mention too. So far, we've only seen horizontal and vertical translations. We can also do this if we had reflections here. So if we had a graph that looks like, or a function that looks like this here, we can graph it by again using our parent function here, y is equal to 1/2 x. And then just using the fact that this negative out here means we're going to be reflecting over our x-axis. Okay, so this function here is f of x is equal to 1/2 x minus 1. And then we're going to graph this -1/2 x. We're going to do that by reflecting over our x-axis here. So that means this point is going to be reflected over our x-axis, so it'll be right about there. This point's going to be reflected over our x-axis, so it'll be right about there. And this point's going to be reflected over it. So we're 2 units up, so we'll be 2 units down here. So we'd still have the horizontal asymptote there, but our graph would behave like this. So this would be our graph if our function were reflected over our x-axis. Now notice that our domain for these 3 guys here is going to be all real numbers. For every x value that we'll plug in to these functions, our function will still be defined. So the domain for this guy is all real numbers. The domain for this guy is also all real numbers. And similarly for this guy here. However, our range is going to differ slightly from what we have for a function of this form. This function here, y is equal to 1/2 x, is exactly of this form. Our range is just going to be all positive numbers greater than 0. Remember, we have a horizontal asymptote here, so we're not going to cross the x-axis, which means y will never be equal to 0. So for this guy, our range is going to be 0 to infinity. Now for this guy here, what we did was we shifted our original function 1 unit downward. So that means our horizontal asymptote is now y is equal to -1. So this means our range is going to be all values that are greater than -1. So all of these output values are going to be greater than -1. And lastly, for this function here, Since what we did was we reflected our original equation over our x-axis here, our range is now going to be all negative numbers, less than 0. So this will be negative infinity up to 0. All right, so now we're going to move on to some more properties of exponents here. So what we're going to do is use these properties to solve equations. Okay, so the first property here says that a to the power x is going to be a unique real number for each real number x. B here says that if we have a to the power b is equal to a to the power c, this will be true if and only if our exponents are equal as well. Right? We also have that for two numbers m and n, m will be less than n if and only if a to the power m is less than a to the power n. And similarly, for a to the power m greater than a to the power n. All right, and lastly, if we have that a is greater than 0, so we have a real number that's greater than 0 and not equal to 1, then a function of this form is the exponential function with base a. So we'll use these properties on the following examples here. For this one, we want to solve the equation 9 to the x is equal to 3. So what we'll do in this case is we will use this property here, b. What we're going to want to do is rewrite this 9 so that we have a base of 3. So we have base 3 on both sides of this guy, and then we can use this property to solve for x. So what I mean is 9 to the power x, we can rewrite this as 3 squared x, right? 3 squared is equal to 9. So our equation becomes this guy. With our properties of exponents, we know that this is the same thing as 3 to the power 2x. Now notice our bases are equal. We have 3 on this side and 3 on this side. So this tells us that this statement is true, so this side is equal to this side if and only if our exponents are equal. This guy has an exponent of 1, so what we can do is set our exponents equal to each other and then solve for x. Doing so, we'll get x is equal to 1/2, and so this tells us our solution set is just going to be 1/2 here. All right, let's look at another example here. We again want to solve an equation of this form here. So we're going to do the same thing. We're going to try to rewrite this guy so that we have the same base, and then we can use that property b to set our exponents equal to each other and solve for x. So the first thing I'm going to do is rewrite this 1 over 5 as 5 to the power negative 1. So we still have that to the power x, and we have that this is equal to 25. All right, now with our properties of exponents, we know again that this x and negative 1 is going to multiply, so we'll just get 5 to the power negative x is equal to 25. All right, and then actually what we'll do is we'll rewrite this 25 as a power of 5. We know that 5 squared is going to be equal to 25. Doing so, now we have that our bases are equal, so we can set our exponents equal to each other. We'll get negative x is equal to 2. And solving for x by dividing by negative 1, we'll get x is equal to negative 2. And so our solution set is going to be negative 2. All right, let's do a couple more. We have this equation here. And again, we want to solve for x here. So what we're going to do is try to rewrite these guys to have the same base. On this side, our base is 2, and on this side, we have 16. So we'll have 2x to the power x minus 7. And rewriting 16, so it has a base of 2, we can write this as 2 to the power 4. Because 2 to the power 4 is equal to 16. Now that these bases are equal, we can set our exponents equal to each other. So we have x minus 7 is equal to 4, and therefore x is equal to 11. So our solution set will just be 11. And lastly, we're going to do the same thing, or something similar, But now we're looking at an inequality. We want to solve this inequality. 3 to the power 2x is less than 81. Now in this case, we're going to use property C here. It says that m is going to be less than n if and only if a to the power n is less than a to the power n. Okay, so what we're going to want to do then is rewrite our inequality so that we have the same base on both sides, and then we can set our exponents like this. So we have a base of 3 on the left-hand side of this inequality, and we know that we can rewrite 81 as 3 to the power 4 here. Now we have the same base on both sides, that's going to be 3. So using that property C here, we get that 2x is less than 4. And then solving for x, so dividing by 2 on both sides, we get that x is less than 2. And therefore our solution set is going to be negative infinity up to 2. Alright, so the last thing we're going to look at in this video is compounding interest. So suppose that a principal of $P is invested at an annual interest rate R, and R will be in decimal form, not in percentage form, and this will be compounded in times per year. Then the amount A is the amount that's accumulated after T years, and that's given by this formula here. So we'll use this formula to solve this problem here. We want to find the amount that would be in an account given $37,000 invested at 2% annual interest for 5 years, and this is going to be compounded semi-annually. So first, let's write down everything that we know. We know that we're given $37,000, so this is going to be our principal. That's going to be P. We also know that we're at a 2% annual interest rate, and we know that our rate R wants to be in decimal form, so R is going to be 0.02. We also know that our T years is going to be 5. And lastly, we're compounding semi-annually. So this means twice a year. So this means that n is going to be equal to 2. So what we can do is plug all of this information into this formula here and get our value for A. Alright, so doing what's inside of our parentheses first, we'll get this here. And so this will be equal to this guy here. Right? And then if you're asked to round to the nearest cent on the homework, doing so for this problem, that'll be this here. Alright. Now, the next thing we're going to look at is what's called continuous compounding interest. So, we have the same setup if an amount of $P is deposited at a rate of interest R, again as a decimal, and we're compounding this continuously. So previously we saw that we were compounding a certain amount of times per year. In this case, we're going to be compounding continuously for a certain amount of years. So then the final amount A in dollars is given by this new formula here. So we'll use this formula on this next example. We want to find the amount that would be in an account given $26,500 invested at a 3.65% annual interest for 4 years. And this will be compounded continuously. So this tells us that we'll be using this formula here. So just be careful with that. If we're ever compounding continuously, we're using this formula. And if you're ever given that you're compounding a certain amount of times per year, we'll use the previous one. So in this case, our P is going to be this guy here. Our rate, we're given 3.65%, but remember we need to write this as a decimal. So this will be this here. And then we know that T is going to be 4 years. So plugging all of this into our formula above, we'll get this here. First thing I'll do is multiply these exponents. And then evaluating this, we'll get, and then again, rounding this to the nearest cent, this would be our final answer. So this would be the amount that would be in an account given that information.